Hey guys, Miss Marusek here, and in this video, we're going to continue to look at electron configurations and orbital diagrams for describing the placement of electrons within an element's electron cloud. Now, in our previous class, we looked at the filling order that those electron configurations and orbital diagrams would have. We said that our S sublevels fill up in those first two columns. Our P sublevel fills up in this section over here on the right. Our D sublevels fill up in the transition metals, and then in the lanthanide and actinide series, we fill up the F sublevels. Now, one of the other things we talked about is the first energy level where we start to see the appearance of some of these sublevels. So, for example, in the S sublevel, we first see it in energy level number 1. For the P sublevel, we first see it in energy level number 2. For D, we first see it in energy level number 3. And for F, we first see it in energy level number 4. So a lot of times, if you can remember where each of those sections are, and you can remember what energy level they first appear in, you would know this order without necessarily having to jot all of this down on a periodic table. So with that said, let's go ahead and look at some examples that they ask us to do here. And the first one says to work the following regarding sulfur. And they first ask us to write the electron configuration. Well, the first thing I need to do is I need to figure out who sulfur is. And so hopefully we remember that that element has a symbol of S. And I would next want to find it on my periodic table. And I see that sulfur is number 16 on the periodic table. And so what that means is that I'm going to need to show the placement of 16 electrons here. And so what I want to do is write everything I went through in this filling order here in order to get to sulfur. Now I'm going to go ahead and write in where sulfur is on here. Sulfur happens to be right here. And so again, I want to read this chart like a paragraph and state everything I went through in order to get to that element. So what I'm going to do for my electron configuration is I'm going to start here at 1s. And I see for 1s that I went through 2 blocks that are labeled 1s, which means that there are 2 electrons in that first energy level in an S sublevel. Now, as we remember, the first energy level can only hold 2 electrons, so that means any other electrons that I add on have to be in a higher energy level. So next, reading this like a paragraph, I come to the second energy level, which again would repeat that S sublevel. So I'm going to write 2s, and I go through 2 blocks of that. So I'm going to put that there are 2 electrons in that sublevel. But we remember that the second energy level can hold up to 8 electrons. So we're going to have a few more electrons that can go in here. And so I keep on following along, and I see that I also would have here 2p. And 2p is 1, 2, 3, 4, 5, 6 blocks across. So that's going to represent 6 electrons there. And I can see that's the total of 8 electrons that the second energy level can hold. So next, any electrons that I add would need to go into a higher energy level. So now we're going to be looking at the third energy level. So next, 3s. And again, that's 2 across. And then I would continue over to 3p. Now, once I get to 3p, I see that I am not going to fill up all of 3p because I don't need to show all 6 electrons. Here, I only need to show 4 electrons. It's the 3 blocks I went through, including the block that sulfur is in, so that's the 4 electrons. Now, if I did this right, my total electron count should total 16. So let's see if it does. 2 and 2 is 4, plus another 6 is 10, plus 2 is 12, plus 4 is 16. So there's our 16 electrons that we were wanting to show. Again, this is an electron configuration. It shows the energy levels that we have, the 2, 2, 3, and 3. And it shows the sublevels, the S, the P's, and then it also shows the number of electrons. So these exponents here of 2 and 6 and 4, those are going to be the total number of electrons in those areas. Okay, so next, this only showed part of the information. Showed energy level and sublevel. It did not show orbital. It did not show spin. That's where our orbital diagram comes into play. Now, in our previous class, we looked at doing an orbital diagram kind of like up and down to show energy amounts. Here, I'm just going to do it side to side, a little more space convenient here. Okay, so to start us off here, I have one S. Now, I remember that S only has the singular sphere orientation to it. There's not other S clouds that exist. It's just that singular sphere. So I'm going to only draw one box here to represent S. I'm going to label it with one S. And inside, I'm going to put two arrows, one up, one down, to represent the individual electrons, but their opposite spins. Okay, in the second energy level, I add on a bigger S cloud, but I'm going to, again, just represent that as a box. And as a reminder, S, I would only draw one box. I'm going to label it with 2S, and then I'm going to draw my two electrons inside. One up arrow, one down arrow for my opposite spins. Okay, now when I get to P, I remember that P could have three different orientations to those hourglass shapes. And so in order to be able to show that, I'm going to draw three boxes here that are connected. I'm going to label them with 2P. And I'm going to draw my 6 electrons inside. Now, as a reminder, we want to follow Hund's rule that says we only put one into each before we double up. But I'll be honest here, on this part, they're all full, so it didn't really matter so much that I filled it in a particular way. But it's a good thing to get in the habit for because it makes a really big difference on the last sublevel that you construct. All right, so now I go to 3S. So again, for S, I only draw one box. And inside, I'm going to have 2 arrows. Now, finally, for 3P4, again, for P, I draw 3 boxes for the 3 different orientations that those P hourglass shapes could have. I'm going to label it with 3P. And I want to show this time only 4 electrons. Now, here it makes a really big difference on how you draw these. Remember, Hund's rule says that I want to put one into each of these before I double up. That will give this element some properties that we don't see in other elements because we have electrons that are unpaired in there. Now, I'll be honest with you. We draw it like this with the boxes because this simplifies what's really happening here. Remember, really, these S and Ps are those spheres and hourglasses. So really, what you would have around your nucleus is a 1s cloud, that's a sphere, with 2 electrons floating in there. Then you'd have a 2s cloud, so you'd have another sphere around it. Then you'd have 2p, which are the 3 hourglasses, so hourglass number 1, hourglass number 2, and then hourglass number 3 kind of coming out at you. Then you would have 3s, so another sphere on top of this. Then you would have the 3p hourglasses that are bigger than the 2p ones were. And you can see that is starting to get really complicated to construct, right? Like, I don't know about y'all, but I'm confused even just looking at that. So the reason why we use the boxes and the arrows is because it simplifies something that otherwise would start to look very complicated very quickly, especially considering here I'm only showing 16 electrons and most of my elements have way more electrons than that. Imagine trying to draw the D clouds on top of this. Like, no thank you, right? It's going to look way too crazy. So the boxes just give us a way to illustrate this where it's a little more simplified and easier for us to follow what's going on. All right, so now they ask us some other questions here that we want to address. The next one they ask is, what are the highest energy amount electrons? Well, remember we have a rule called the off-bow principle. Off-bow principle states that we fill orbitals of lowest energy first, which means the highest energy amount are the last written. So if I look which electrons were the last thing I wrote, that would be the 3p4s. Those 4 electrons have the highest energy amount out of any of these, including a higher energy amount than 3s, because remember the shape does contribute somewhat to the energy amount. All right, so now the next question asks, who are the outermost or valence electrons? To decide this, I'm going to look at what electrons are in the highest energy level number. Now, this could be the same as the last written, or it may be different. You might also see a couple of different things that have the highest energy level number. So I'm going to look at the 1, the 2, the 2, the 3, the 3, and I'm like, out of those energy level numbers, 3 was the largest number we saw. That means those would be our valence electrons. So we had 2 types of electrons that had that. That means we had the 3s2s and the 3p4 electrons that were all valence. They were all in the 3rd energy level. So now, to get my count of those, I just simply add up those exponents together. 2 plus 4 would mean that I had a grand total there of 6 valence electrons. Now, I'm going to mention something some of you might remember back from middle school. Typically in middle school, they teach you that every single group has a certain number of valence electrons. Usually they say, hey, group 1 has 1 valence electron, group 2 has 2. We skip over the transition metals. 13 has 3, 14 has 4, and you keep on working over until group 18 has 8 valence electrons. That's a pattern that most of the time you learn back in middle school. Well, going back to that pattern for a second, look at sulfur. Sulfur is in group 16. If you use that pattern for middle school, you should figure out that sulfur would have 6 valence electrons. And look what we just wrote down. It has 6 valence electrons, right? So all those things that you learned back in middle school aren't going away. It's just now we're kind of adding more information to them. Now, there's one other question we can answer for right now, and that is, how many unpaired electrons does sulfur have? So if I look here in these orbitals, most of the orbitals are paired up with the exception of these last 2. They do not have a pair or a partner in their orbital. So that means that there are 2 unpaired electrons that are in sulfur. If they did have partners there, you could even say that something had no unpaired electrons. So you can have a various numbers there for that unpaired electrons, depending on what your element was and how far over within a particular sublevel you're filling up. All right, we're going to save this next set of questions here, this F through I, for just a little bit. What I want you to do is I want you to take just a moment and see if on the next example below this for strontium, I want you to see if you can do the same pieces that we did up above, which would be A, B, C, D, and E. So what I want you to do is to take a moment and pause this video and see if you can figure out A, B, C, D, and E for strontium. So go ahead, pause the video, try it out. Okay, did you pause it? Did you try it out? I hope you did. Let's see how we did. So for your electron configuration, you should have had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and 5s2. Notice that this one had more electrons in it because strontium, Sr, is a bigger element. Strontium has 38 electrons in it that we needed to show. Now, on our orbital diagram, that meant we had 38 arrows we needed to draw. And hopefully you figured out that this did include a D sublevel, and so you did have to draw the 5 boxes to represent that D sublevel filling up. So hopefully you did okay with that. And if you notice, you had all the way to 5s, and in that box, they were all paired up. So highest energy amount electrons would be the last written. That was 5s2. Outermost or valence electrons, those are in the largest energy level number. Well, I had 1, 2, 2, 3, 3, 4, 3, 4, 5. 5 was the biggest, and I only had 5s2 there, and so that would be 2 valence electrons, which should make sense if you remember back from middle school that any element that's in group number 2, like strontium, would have 2 valence electrons. Here I had no unpaired electrons. Everything had a partner all the way to the end. Now, some of you are starting to pick up that this pattern is the same pattern every time. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That pattern stays the same for every single element. The only difference is where we end in that pattern. How many ever electrons we have, that's where we're going to cut off that pattern. So keep in mind that you're always going to see that same pattern over and over again. So if you really start to familiarize yourself with that pattern, it will definitely help you as you're trying to write these electron configurations and orbital diagrams. Now, the rest of the questions on both of these two examples referenced what happens when things become ions. So what I want to do is I want to go ahead and look at what you see on the next page about forming ions. If you were having to predict the charge of an ion, for a metal, most of our metals will lose electrons to become what is called isoelectronic with the nearest noble gas. Isoelectronic means it ends up with the same number of electrons. And when they lose those electrons, the ion does end up becoming a little bit smaller than whatever you started out with. There's a couple reasons for that. First off, a lot of times you end up losing the valence energy level, but also you end up reducing repulsions from the number of electrons. And so that can help to suck in that electron cloud. On the flip side, your nonmetals tend to gain electrons to become isoelectronic with the nearest noble gas. You notice on both of these, we're going to try and look like a noble gas if we are predicting. And that is pretty common for an atom becoming an ion. A lot of times it ends up wanting to look like a noble gas with regards to the number of electrons it has. Now in this case, when they gain electrons, they become larger. Why? Because you're adding repulsions into that electron cloud when you add additional electrons, and that kind of pushes out on everything for it to become larger. So we end up seeing some patterns that end up existing with regards to this idea of losing and gaining electrons. And so I filled out a chart down here for y'all. If you are in groups 1, 2, or skipping over to group 13, you will notice that I have the valence electrons as some energy level, whatever that outside one is, and then S1, S2, or S2P1. And so that would be a valence electrons of 1, 2, or 3 for group 1, 2, and 13. In order for those to look like a noble gas, it is much easier for those to lose electrons versus gain them. It's a little more convenient, and we'll see that on our periodic table here in just a little bit. And so what happens is that these usually take on a positive ionic charge. You notice for group 1, positive 1 is its common charge. Group 2, positive 2, and group 13, positive 3. When it becomes an ion, say in a compound, that is the common charge that that ion would take on. And it does end up being smaller than the original atom, again, because you're losing electrons, and so you're losing repulsions. However, when you're talking about the nonmetals on the far right-hand side of the table, and notice I did specify here nonmetals because the metals under that zigzag line are going to do some kind of weird things, and we'll talk more about those on another video. But you notice for these, you'd have your energy level, you'd have S2P3 or S2P4 or S2P5. Now, the idea is, again, to look like a noble gas, which would have S2P6, and so we're going to gain some electrons in order to get that configuration. You notice here, if you only had 5 valence electrons, then it's convenient to gain 3. If you have 6, it's convenient to gain 2. If it's 7, it's convenient to gain 1 in order to look like the nearest noble gas. When it does so, you notice our ionic charge becomes negative. Just like we've talked about previously, when I gain those negatives, now I have more negative electrons than I do positive protons, and so the charge should become negative. All of those do end up larger because, again, I'm adding those repulsions in, and that's going to cause my electron cloud to grow in size. So now, with all that said, Let's go back to the examples that we saw on the previous page for a moment and kind of see what those ones would do when they become an ion. So we're first going to go back to our sulfur example. Now I'm going to actually look at a periodic table with sulfur on it. And if I am trying to predict the charge of an ion, if it's not one that they've already told me, then more than likely it's going to want to do its best to look like a noble gas. Well, let's think about the two things that sulfur could do. Sulfur could either try and lose 1, 2, 3, 4, 5, 6 electrons and go back and look like neon, or it could try and gain 2 electrons and go forward and look like argon. Now let's think about this numerically for a second. What sounds easier? Losing a whole bunch or gaining just a couple? I don't know about y'all, but losing 6 sounds way more complicated than just trying to gain 2 more, right? So more than likely, this sulfur would gain 2 electrons to look like argon, which should make sense because we just said that nonmetals tend to gain, and if you notice, this is on the right-hand side of our zigzag line that separates our metals and nonmetals. So here's what I'm going to do. I'm going to put on here that the most likely ion for sulfur is a sulfur -2 charge. Why? Because we are going to gain 2 electrons to go forward and look like the nearest noble gas. Now they ask us a question down here. What would the new electron configuration for this sulfur ion be? Well, think about where those 2 electrons would go into. And actually, I'm going to have you look at the orbital diagram for a minute. Notice how we had those 2 unpaired electrons that had some empty space in here. Wouldn't it make sense to stick those 2 electrons into that 3p and end up filling it up? Yep, and that's exactly where they're going to go. I'm going to end up here with 1s2, 2s2, 2p6, 3s2, and 3p instead of 4, we're going to have 3p6. Now it asks, would the resulting ion be larger or smaller than the original atom? Well, we added some additional negative electrons. That's going to cause us to have more repulsions in the electron cloud, and that's going to cause us to push out a little bit. So this should be larger than the original atom. And it says, with which noble gas is the sulfur ion isoelectronic? What noble gas would have this exact same electron configuration? Well, as we just said, we're going to gain those 2 electrons to go forward and look like argon. So that's going to be the noble gas that we are isoelectronic with here. All right, let's do the same thing for our strontium example now below. And I'm going to put back up here what my answers were for this. And so on here it asks, hey, what is the most likely ion for strontium? Do we lose or gain electrons to form the ion? Well, remember, strontium being a metal, what does it like to do? Does it like to lose or gain electrons? And hopefully you remember, we just said a little bit ago, that strontium likes to lose electrons, which makes sense. We could either try and go forward to look like a noble gas, or we can lose those 2 electrons and very quickly go back to a noble gas. It's much more convenient for this to lose than for us trying to gain. So what that means is that here the most likely ion for strontium is going to be strontium +2. Here we're going to have lost those 2 electrons to end up becoming that ion. So it asks, what would be the new electron configuration for the strontium ion? Well, let's think about the 2 electrons that we would lose. It doesn't make sense to lose things on the inside because I would have a really hard time trying to give those up to something else. It's going to make a lot more sense to lose these ones that are on the outside. Anytime we're adding or removing electrons, we're always going to do so from the valence electrons. So what I'm going to do here is I'm going to rewrite my electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, but I'm going to stop there. I'm not going to write that 5s2 because again, Those are the electrons that I would lose in order to become the ion. It then asks, would the resulting ion be larger or smaller than the original atom? Well, think about it like this. Not only did I lose electrons, so I lost repulsions, but I literally just lost the entire 5th energy level. Like, I now only have 4 energy levels, where before I had 5. So I am definitely going to be smaller here than what I was before. And then finally it asks, with which noble gas is the strontium ion isoelectronic? So let's think about that on our periodic table for a second. When that strontium loses those 2 electrons, it goes back over here and ends up looking like krypton. The electron configuration that we wrote here for the strontium ion is the electronic configuration for krypton. They're one and the same. All right, I hope we're feeling a little bit better with looking at electron configurations and orbital diagrams. We're going to see some more examples in our next video. Bye, guys.